Lyon, and Adrian Chavez. And we're going to be presenting the NASA CubeSat design competition. So our project description is we're part of the Earth Explorers Club, and we're designing and manufacturing a 3U Eagle satellite in order to compete to the NASA FunSat competition, which will be held in 2018. Part of the requirements that we have to meet is that the satellite must not interfere with other satellites, and it must meet our budget requirements for the club. So this is an artistic illustration of concepts that we come up with. So our motivation is to improve on previous work from previous year presentations. So also the satellite is able to we want the satellite to record weather patterns and get thermal images. Also, we want to win the competition because the top 3 people who place in the competition get their satellite sponsored to launch into orbit. And last year's 2016 competition was able to do that, so we want to meet their standards and exceed expectation. So objectives, part of the objectives on improving on the previous designs were the structural design and also the optics. So we want to improve internal structure, decrease the rate of external structures, and then develop mechanical gear systems for the optics. We also want to implement and experiment with the communication system and an attitude control to see if it's working and what we can do to change it. Also, we want to integrate the payload into the communications and power systems. Also fabricate the satellite to find and launch goals. So,
brief history on Pico satellites, or in this case CubeSats, was begun in California Polytechnic University in 1999, and it allowed students the access to space. There are 3 different classes, which all range from 1U to 3U. Ours is going to be the 3U, like Alex said, which is a 10 by 10 by 30 centimeter satellite. And what it does allow us to do is take advanced thermal imaging and images that allow us to move forward in space technology.
So the standards that we follow are set by the NASA Design Competition, as well as some FFA regulations. These encompass basically every component of the satellite, including what we just did for our project, which was the gear design and the internal structure, and we'll go into this further once we get to the analysis.
The structure, so right here we have the external structure, which usually, in our case, is going to stay the same compared to previous teams. On the left there, you see the inspiration towards what we wanted to do with a fully removable structure. We did do some design alternatives. The first one was the previous year's, which is the senior team that's presenting next. And what it had the pros where it was extremely lightweight, but it also wasn't as structurally sound as we wanted, and the access to the internal components just wasn't up to par. So we came up with previous design, preliminary design that integrated a shelving system. Unfortunately, again, we wanted to adhere to the no loose wiring and things of that nature. So the design we came up with was fully carbon fiber internal structure that is completely removable and gets locked into place when the satellite does go into space, as well as a contact connection at the bottom. Once you force it in and lock it in place, the contact connection stays in place, which allows for easy access for repairs and in case of catastrophic failure. Underneath, we see the contact connection and the camera system. This allows for the optical lens to be fully accessible at all times for the satellite, as well as the contact connection. We also took into consideration the antenna connection on this contact because of the carbon fiber conductive properties. Some of the simulations we ran were a worst case scenario, and this is just on the internal structure without the external structure. Go ahead, next one. And this is at space, which is 2.7 Kelvin. We ran a factor safety of 1.6, which is just for, like I said, for the internal structure.
Now for attitude control, usual ways of control the satellite up in space is kind of difficult due to the limitations of sizing. Since it is 10 by 10 by 30 by partner said. What this project is going to be doing is using magnetic torque bars, which consist of a metal rod wrapped in copper wire, and it's going to be located on each principal axis. The additive control system consists of two subsystems, which is additive determination and the actual additive control. Additive determination is a key component because we need to know where the satellite stands up in space. This is made possible through the sun sensor and the LSM-9D0 right here. The sun sensor will tell you where the satellite stands in respect to the sun, and that will help the control of that as well. And then for additive control, what it is the magnetic torque bars create an electromagnet that communicates with Earth's magnetic field and realigns itself up in space. After doing some analyses on the orbital parameters, this is what we obtained. Satellite being like 600 kilometers above the surface of the Earth.
Okay, so for the optical system, I was given a lot of information from previous Near Earth Explorer Club teams and senior teams in terms of the cameras that they had selected, and they also were able to design the lens and the optical tube. So I was in charge with designing a mechanical gear system that will rotate each selected camera into position in front of the lens. To do this, I decided to use a stepping motor to give the initial driving force, and we're going to use a straight bevel gear system to transmit that force from one axis to another, and that will rotate this platform, which will have the three cameras attached, in front of the correct lens. Go ahead. So these are some of the selections that were made by the previous satellite teams. So I didn't decide this. This was all given to me as parameters to make my design off of. This is the TTL camera, the image sensor, and the thermal camera. This one right here is very small. It's only 6 by 4 millimeters, which is very, very tiny. The biggest one is 20 by 28 millimeters. The biggest power that is consumed from these cameras is from the image sensor, which is 0.644 watts. And as you can see, we also have details of the mass and the cost for the cameras. Okay, so to design the gear system, I relied entirely on AGMA calculations. Again, so this is straight bevel gear system. This is for the contact, and that's for the wear. And I basically did a power rating to determine whether the gears could sustain the force delivered by the stepping motor. Alright, so just a little preliminary design choices that I made based on dimensions. We know that our satellite is 10 by 10 centimeters, and the internal structure is approximately a centimeter, so automatically our available space has been reduced to about 8 centimeters inside the satellite. So this is the platform. It is 55 millimeters in diameter, 5 millimeters thick. I'll show some simulations on that in the next slide. Go back, sorry. So here you can see that there's one camera drawn in. This is the image sensor. This block right here is the thermal, and that one's the TTL. And this right here is the actual on the opposite side. That is the 20 millimeter gear that was designed. So, based on kind of what I've talked about already, I was able to choose the desired diameter of the gears, the amount of teeth that I wanted, and based off that, I calculated the diametral pitch. The relief angle was chosen just based off AGMA standards, and the RPM was given to us based on the fact that we know the stepping motor is 5 volts at 0.26 milliamps. That gives us 1.3 watts of power. So as I went through the AGMA analysis, I found that changing the face width of the gear was actually the most detrimental aspect, because at 1 millimeter, which was my initial choice, the system actually failed. So in order to get the correct safety factors and the horsepower ratings, as seen over there, I had to increase the width to 2 millimeters. So the final gear design, we have the stepping motor, which is going to be 5 volts, 260 milliamps, 1.3 watts. It has 48 steps per revolution, roughly 0.002 horsepower, which again, it's a very small stepping motor at 40.9 revolutions per minute. So the two gears, again, will be in a straight bevel system. They're identical miter gears, which means they have the exact same dimensions and qualities. So they'll each be 20 millimeters in diameter. The diametral pitch will be 25.4 teeth, roughly, which based on catalogs, you can probably select one out either 25 or 26. And the number of teeth at 20, and as I just described, the most important thing, the face width, which is 2 millimeters. And the total assembly, stepping motor, platform, gears, and 3 cameras only weighs 73 grams. And that is really important because the amount of payload that we are allowed in the competition is only 4 kilograms. Alright, so this is just a von Mises stress analysis of the platform to make sure that it could hold the weight of the cameras. So I said this end was fixed because it will be in a bearing that will rotate, and forces were applied on the opposite side. Just for analysis purposes, I viewed them as a uniform pressure on top of it at 0.2 newtons, which was the weight of the 3 cameras. And the one on the right shows the deflection, which really wasn't a concern for us to begin with, but just to be sure, as you can see, we had a 0.002 millimeter deflection, which is very small. Alright, so this is the final assembly. Stepping motor, the 2 gears that were designed, the platform, and the 3 cameras mounted on top. One thing I would like to note about this is that in order to test it, previous teams used a weather balloon and then it was tethered, and they were able to take a picture. However, they were only able to use 1 camera. So my goal for the testing is to be able to rotate between each camera and snap a picture using the same weather balloon assembly. And for the future, moving forward for the next part of this design, I just have to select the bearings and design a casing system that will fit inside.
Thank you, Scott. So I'll be in charge of the subcommunication implementation. This subcommunication has been brought up from previous groups, and we'll be using a BeagleBone microcontroller. So this allows us to communicate with the ground station that's been established at the FIU main campus Green Library, and also it allows us to demand command information from the satellite, given weather patterns, thermal images, and it will transmit data in real time. So for the global design, the Earth's atmosphere, all this information will be given to the public. This gives us a global engagement to solve key issues. Also, we'll be powered from solar cells, and everything is made from readily available materials. And we'll also make manuals in multiple languages to communicate to more people. So here we have the Gantt chart. Yes, as mentioned earlier, we will present in April. But again, since the competition is in 2018, we will give this project to another senior design team and have them improve on their final design. So by the time 2018 comes, we can win the competition and launch our satellite up into orbit. We're currently in the development phase. So as a conclusion is, for this semester we have met all our objectives. Our structural weight has decreased with the use of carbon fiber, and our internal structure is designed to detach more efficiently. We went everything with AGMA design for our gears. Testing will be performed, and then further force analysis and deflection are under research and development. Thank you for the time and references. Thank you, and we open up the floor for questions.
So you guys only designed the gear structures, what it looks like for the actual CubeSat? You're gonna let the rest of the project, you're gonna hand off the rest of the project to a future team? Or did you guys also design, change the external structure of the CubeSat?
The most of what our design, we designed the removable internal structure, which basically has the components already attached. So instead of having, if we wanted to do work on the current satellite that exists now, you would have to take out each component individually, unhook it, the whole 9 yards. This design that Adrian came up with, everything will be plugged into the internal structure, and with one motion, the entire thing will be slid out and then out of the power contact. So our team designed that structure, and yes, primarily the rotational device for the cameras. However, what we built on from the previous senior, they did all the power subsystem, they did the external structure, and they did the preliminary calculations for the attitude control. So potentially what we're handing off to the next senior team, they're going to have basically the ground control station to work on and the microcontroller programming and stuff like that.
Do you guys have any grounding requirements between your external structure and your internal structure?
No, I believe the only thing that is necessary is the solar panels to power the batteries that are on board, and then the internal structure is where the grounding happens with the batteries, the polarity of the battery.
Yeah, but my point is your structure grounded? You can have grounding through your pins for your wire work for your solar panel, but your structure isn't grounded to anything. So you can't dissipate triboelectric energy or triboelectric charge that's generated on your structure, and that could potentially cause like a transient on your avionics system and actually just fry everything.
I haven't taken that into consideration.
Yeah, so I would say like look into if you have any requirements for that, because I'm sure your external structure to the vehicle needs to have some sort of grounding requirement, and if your internal structure coming off of the vehicle by itself, then you probably need some sort of grounding requirement for that so you don't damage your own avionics.
Thank you.
The other thing is, you guys said that your external structure protects you guys from catastrophic failure? Like,
No, I don't think I mentioned that. I think what I did mention was that we did the simulation analysis on the internal structure alone, because the external structure has weld joints and all of those, and it's a pretty sturdy structure, where we don't need to take into consideration what would happen if it's a catastrophic failure via the two, just on the internal structure. Kind of what I was getting at.
okay. Well, if it fails catastrophically, it's going to fail regardless, right? I think more importantly is, will your external structure hold up to your failure? Because you don't want to damage other payloads on your mission.
And we'll take that in consideration because the previous team did take care of the external structure. That was part of their senior project. We were just working on the new generation.
Last question, are you worried about snagging any wires?
Well, we're trying to avoid as many wires as possible with that connection, making all of the microcontrollers as close to the power connection as possible, eliminating some wires. So no, we're not going to be worried about snagging any wires. If we're meaning by like taking out the structure, everything's just going to be sprung contact connection, so that we don't have to worry about what wires being in between the external structure and the internal structure.
What about your cameras to your avionics?
The cameras and avionics are going to be mounted inside that structure with 3D printed shelving systems, so we don't have to take into consideration. The only time we would have to worry about that is if we were taking the internal structure out for maintenance or repair.
Sorry, I would look into strain relief for your wires and potting your solder terminals, because they'll break under flight loads for sure, because they're not meant for that. They need to have secondary or like some form of damping if that's what